Okay.
Hi, Javier, please share your slide. Okay, he is mute, I think.
Munna, you can start it. Oh, sorry, Munna. Yeah, sorry, you can start it off.
But I am not able to see his slides, right?
Yeah, he will put his slides. Okay.
Okay. So probably
He's on.
you are muted, Javier.
Can you hear me now?
Yeah.
Yeah,
Please
okay.
share your slide so that I can introduce you.
And you see the slides now?
Yeah. So let us start.
Okay, sorry about that. I got disconnected by mistake.
Welcome to our APRG seminar. Today our speaker is Javier Parcet from Instituto de Ciencias Matemáticas. Okay. And he will talk about Fourier and Schur idempotents. And I request all the participants to mute their mic, okay, and listen the talk very with rapt attention. So let us, with this, I invite Javier to give his talk.
Thank you very much. I would like to thank the organizers for inviting me to give this talk. It's very nice. I haven't been physically to Bangalore, but it's nice at least to give a talk online. So my talk today is based on joint work with Michael de la Salle from Lyon and Eduardo Tablate, who is my latest PhD student in Madrid. And it's about Fourier and Schur idempotents, meaning Fourier and Schur idempotent multipliers. This is related to a very traditional problem in harmonic analysis, which is about the convergence of Fourier series and integrals. And the talk today is related to a non-commutative extension of the known results, as we will see, which have some implications in geometric group theory and operator algebras. Okay, so let's get going. The first block of the talk, it's about presenting the objects, which are Fourier and Schur multipliers. So let's go to the classical setting in first place. So if I consider a function on some locally compact abelian group G, then the corresponding Fourier multiplier is an operator acting on the dual group of G. So let's call it G hat, in such a way that acting on a function f, it is the result of taking the pointwise product of M and the Fourier transform of f, and taking the Fourier inverse of that, okay? So in the classical groups, like the torus, whose dual group is the integers or the integer lattice, or in Rn, and these multipliers look like this. So if I remove M here or there, this is nothing by the Fourier series or Fourier integral representation of f, okay? So the classical problem is about Fourier LP summability, meaning that we are interested in finding which sequences of MJs, like these ones here, converging to one, have the property that we can recover any element f in LP as the limit in LP of TMJ f, okay? So this is the very general problem. It is, of course, out of reach to give a full characterization of those, because this would imply the solution to very long-standing conjectures in harmonic analysis, and it is not understood to be doable so far. But let me go to the particular case in which the MJs are chosen to be characteristic functions of certain domains omega j, okay? So this means that in our approximation, for instance, here or here, okay, what we are doing is selecting which frequencies are going to be part of our partial Fourier sum or partial Fourier integral, okay? So this is a characteristic function, so we just pick some frequencies but not others, okay? So in the particular case of Rn, the problem essentially reduces to know which Fourier multipliers associated to the characteristic function of a domain are LP bounded, because the problem is dilation invariant, and we could have picked here dilations of a fixed domain omega. Okay, so let us think for a while which is which domains omega lead us to LP-bounded Fourier multipliers. The first example is the Hilbert transform in the real line, which is given here, and this is a very well-known operator. And let me give you, before going on, a small picture of what I have in mind. So we have, for instance, in 2 dimensions, we have the plane, and then we can consider a Fourier multiplier which has the value 1 in a semi-space and the value 0 in the other semi-space. Okay, so this is essentially the result of taking the Fourier, the Hilbert transform. Sorry, this is not the Hilbert. Sorry. It's not gonna help me doing it. So let me do it in a different way. So we have here our semi-space, and what we want is, is to, is to consider the Hilbert transform in this direction, right? So this is a one-dimensional Hilbert transform, and the rest is acting as the identity map. So essentially, a one-dimensional Hilbert transform allows us to consider semi-spaces in higher dimensions, and we could also consider combinations of those. So that, for instance, if I consider the combination of all these Hilbert transforms, this means that I would get the value 1 in this triangle and 0 elsewhere. Okay, so this is, of course, an LP-bounded Fourier multiplier. And for the same reason, any convex polyhedron here can be understood as a solution of this Fourier LP summability problem. Okay, so for convex polyhedra, this is a very easy problem. And then what came out after that is, what about dilations of the unit ball in Rn for dimensions greater than 1? So the original conjecture was that this was an LP-bounded multiplier whenever P is close enough to 2, meaning that 1 over P minus 1 over 2 in absolute value is less than 1 over 2 times the dimension. But what came as a big surprise is Fefferman's theorem for the ball in 1971, where he proved that whenever n is greater than 1, the ball multiplier is LP unbounded for every P not being equal to 2. So Fefferman's proof was based on a very well-known lemma due to Meyer, in which he proved that whenever if we assume that the ball is an LP-bounded multiplier, then certain square function inequality for Hilbert transforms should be LP-bounded as well. So he was able to produce a sequence of rectangles in 2 dimensions pointing in the directions of these Hilbert transforms, and then using a Kakeya construction, or a so-called Besicovitch construction, he was able to disprove this result. In fact, the proof of Fefferman applies as well to any domain omega with non-flat smooth boundary. Okay, so the domain doesn't have to be a ball. Anything which has a non-flat boundary in some region of it would be LP unbounded for every P not being equal to 2. Okay, so this came as a big surprise. And now let me jump over the noncommutative setting to see what is the problem that we are trying to address. So I will be fixing G to be a unimodular Lie group for the moment. Mu is the hard measure of this Lie group, and lambda is the left regular representation, meaning that lambda of G is just the unitary acting on L2 of G by left translation. So a function phi goes from the original function to the left multiplication by G inverse in its argument. Okay, so this is a very well understood unitary, And using these unitaries, lambda of G, we can construct the corresponding Fourier series in which we replace the classical characters in classical harmonic analysis by these unitaries. So here f hat is a function which is continuous and compact supporting the group. And then the group for Neumann algebra is nothing but the weak operator closure in B of L2 in the linear operators which are bounded on L2 of the linear span of these Fourier integrals. Okay, so whenever the group is abelian, L of G is nothing but L infinity of the dual group. Okay, this is very easy to check. But in general, when the group is non-abelian, you have to work with group for Neumann algebras to resemble what would be L infinity of the dual group, because there is no dual group for a non-abelian group G. Okay. Well, whenever E is the unit of the group, the hard trace is just determined by the trace of F being a Fourier integral of this kind, is just the Fourier coefficient at E. So it's this function evaluated at the unit. This is exactly what happens in Rn. So we are just copying to some extent the definition of the hard trace or the hard measure in Rn. And what is a Fourier multiplier? Well, if we fix a function m in our group G, and we want to define a Fourier multiplier in our group for Neumann algebra, we just need to produce a linear map acting on elements of this kind, so that the Fourier coefficient at G is nothing but the pointwise product of m of G, f hat G. Okay, see, this is again resembling the classical definition of Fourier multiplier. And this was studied for the first time in the pioneering work of Hagerup in the late 70s, and also Colin Hagerup in the mid 80s. But in the last...
So your slide is not clear. So the thing is, maybe you can turn off your video if it helps.
Sorry?
Your slide is not clear. We are not able to read it clearly.
So
it is blurred.
Now can you read it?
Now it is, I can read it. But the thing is, probably if you will turn off your video, it may help see it.
So I don't use the complete screen?
No, what I'm saying that you can turn off your video. Probably it will help a little bit.
Turn off the video? I don't...
Video. No. Okay, do again you share the screen then. I don't know, it's probably your internet connection is not that great.
So you are not seeing the slides properly?
Slides, we are seeing the slide, but it is not clear. Now it is clear.
Okay.
Yeah, now it is clear.
Okay. So what I was saying is that this was introduced by Hagerup in the late 80s, but in the last 10 to 15 years, the LP theory corresponding to these Fourier multipliers have been strongly investigated by my peers, Junge, May, Ricard de la Salle, myself, and many others. And this has been useful in connections with geometric group theory, functional harmonic analysis, and operator algebras. Okay, so let me get going. Do you see now the screen properly?
Yeah. So can you go back to the previous slide? I have to ask.
Okay, I will go to complete slide. Is it okay now?
Yeah, previous slide.
Okay. So these are what I introduced in the last slide are Fourier multipliers. Let me now introduce what are Schur multipliers. Schur multipliers are very easy to define. If I have a function defining 1, 2, up to n power 2, then the corresponding Schur multiplier acting on an n by n matrix is just the n by n matrix in which I multiply each entry by the evaluation of m at jk. This is very easy map. I can, of course, extend it to matrices indexed by the whole integers, okay? So these matrices are bounded operators in L2 of the integers. And I can even extend this definition to other operators acting on L2 of omega for some sigma finite measure space omega. I just need to define M to be a symbol in omega times omega. And this operator SMT will act on operators T, which admit a kernel K of XY. Okay, so this SMT of F at X is just what it would be T of F at X, which is KXY F of Y dy, but I multiply this kernel by M of XY pointwise. So it's exactly the same kind of definition as I was using for the classical Schur multipliers. And we should have no worries here because operators with kernel are dense in the relevant topologies we will be working with. Okay. So besides Fourier multipliers, the problem here is to understand which symbols M lead us to SP-bounded multipliers. SP here is the Schatten P class, so the natural LP space over the matrices, which is given by this. So the norm of SMA in the Schatten P class is the trace of this object, which is the absolute value of SM power P, if you wish, SMA star SMA power P halves, everything to the power 1 over P. Okay, so that's the definition of the Schatten P class. And the problem is to decide whenever this is less than CP times the norm of A in SP. Okay, as we will see, this problem is even more general than the Fourier multiplier problem. Okay, this we will see in the next slide. So I want to look at a particular class.
I'm sorry to.
Yes?
I'm sorry to interrupt you. You lost the connection for 1 minute. Sorry, few seconds. So
yes,
we couldn't hear you.
Okay, so I was saying, did you hear about this box in
SMT?
Yellow? Sorry. Hello. Hello.
Munna is not here.
Yeah, there seems to be some problem with the connection with Munna.
Munna is not connected.
Yeah,
I think I just got disconnected as well. So maybe you could continue.
Oh.
Okay.
Munna will get connected back. We have some problem in our department right now, I suppose. Thanks.
Okay.
Sorry.
So let me continue. So I was saying that Fourier multipliers are in a sense less general than Schur multipliers because the problem that I was addressing here for Schur multipliers is more general than the one for Fourier multipliers. Okay. So let me justify that in the next slide. So I will consider a particular class of Schur multipliers, which are so-called Tablate symbols. So M of xy is of the form little m of x minus y. Okay, that is in Rn. If I am in any other group, instead I will be working in symbols of the form little m of G H inverse, where G and H are elements of the group. So Tablate symbols are a particular class of what I call here Hertz-Schur multipliers. Okay, so for this class of multipliers, a result which goes back to 2011 by Neuwirth-Ricard and was extended by Caspers de la Salle in 2015 tells us that Schur multipliers and Fourier multipliers preserve their norm. I am writing here CB to reflect that I am talking their norm in the operator space setting, but we should not take care of that. This is not so much relevant for this talk. So let us just say that whenever P is between 1 and infinity, the LP to LP norm of the Fourier multiplier is equal to the SP to SP norm of the Schur multiplier in Rn or in any other amenable group. Okay, this is very important. In any other amenable group, this is true as well. For non-amenable groups, this is another story, but a local result is true as well. Okay, do you follow me so far?
Yeah, may I just one question?
Yeah.
So you said Schur multiplier is a particular case of Fourier multiplier. May I ask how it's connected, or am I missing something here?
Yes. This is this is the box I am putting here. There is some echo for someone is using the audio, and I hear myself.
Can everybody mute their mics, please, except the speaker? Thank
So okay, so let me continue. So the logic of this result is that if I take a Fourier series, for instance, with Fourier coefficients in the integers, so this is a function in L infinity of the torus, then I send this function to the matrix which jk entry given by the Fourier coefficient of f at j minus k. So this is a bounded linear operator in L2 of the integers. And it turns out that this map is a star homomorphism, meaning that it is a linear map, it preserves products, and it preserves adjoints, okay? So extending that to be an LP isometry for P finite requires the amenability assumption that we have in this result. But this is somehow the way in which we relate Schur multipliers and Fourier multipliers by this map. Okay. I hope to.
Yeah. Thanks.
Yeah. Okay. So let me continue. So what about non-Tablate Schur multipliers? So those for which m of xy is not of the form little m of x minus y. These are even more general than Fourier multipliers. And the known results are very limited. The most important result in this line is the so-called Grothendieck-Hagerup characterization, which tells us when such an object is bounded in B of L2, or if you wish, when it's bounded in SP for P equal to infinity. Okay. So the solution is that this happens if and only if m of xy can be written as an inner product in certain Hilbert space K of a family of vectors ux and a family of vectors wy for almost every xy in your measure space X, okay? And the situation is that these families of vectors have to be uniformly bounded. And the supremum of these norms is exactly what gives you the norm of this operator as a Schur multiplier in S infinity. Okay, so this is not relevant for this talk, but this is the most important result in this direction. Very recently, despite a very limited literature on SP boundedness for P finite, we have found with our group in Madrid and also Tao Mei with his group in Texas, noncommutative forms of the Hormander-Miglin theorem and the Marcinkiewicz theorem for multipliers in the non-Tablate Schur multiplier setting. So again, this is not relevant for this talk, but I wanted to at least mention these results so that you can go to the literature in case you're interested. Okay, so what are the main motivations for this talk? The first one is this map here. If we consider a pair of points in the n-dimensional sphere, okay, and I send them to the characteristic function of points for which the inner product of x and y is positive, okay? So if you wish, whenever x and y belong to the same hemisphere, okay, then this operator was studied by Laforgue and de la Salle in 2011, and they were able to prove that whenever 1/2 minus 1/p is greater than 1/2n, this is an SP unbounded operator, okay? And of course, the situation is very similar to what Fefferman had at the beginning of his multiplier theorem for the ball. This was known, but for p very close to 2, it was unknown whether the operator is bounded. So we are trying to address this question and to answer whether these operators are bounded or not only for harmonic analysis reason, which is very natural, but also because it has connections with geometric group theory. Okay, so that's the first motivation. The second one is, what can we say about Fourier idempotents on Lie groups? So we have seen that Fourier idempotents in Rn are polyhedra, essentially, because the boundary has to be flat. But if you have a domain in a Lie group where the geometry is already curved, what do you state to be flat? What is a domain whose boundary is flat in a Lie group? This is something which we didn't understand, and I have been searching this question for a long time. So we aim for a geometric characterization of those domains leading to an LP-bounded Fourier multiplier, and if possible, a group theoretic characterization as well. So this is what this talk is about. So let me now jump to the second block, which is about Schur multipliers. So I will be fixing here a domain sigma in Rn times Rn. So this is a C1 domain. The boundary is C1. And let me paint a little bit. So then what you have to keep in mind is that we have here a matrix, okay, with index x and y. And then I have a domain sigma, like this one, and I have a point in the boundary, okay? This is a point in the boundary. So the point is xy. So n of xy is the normal vector to this boundary point, and n1 xy is the first n coordinates of this normal vector, and 2 xy is the second n components of these normal vectors, because this is a 2n dimensional vector, okay? So we will say that xy is transverse when both n1 and r2 are non-zero. So for instance, the one I am drawing here is transverse because no component horizontal or vertical are zero, okay? So it's an diagonal vector, let's say. So this being said, we can state the main result of the talk, which is the following. We can characterize in a local form the SP boundedness of these Schur multipliers by just fixing a local neighborhood of this point. Let's call it U and B, in which I am putting the rows of around my boundary point in the neighborhood U and the columns in the neighborhood B, okay? And then I want to give a characterization of SP boundedness of my Schur multiplier only in this box, okay? Only in a small box around a point. So the theorem I'm going to state is a local theorem. So it is equivalent for any P not being equal to 2 between 1 and infinity, that this idempotent Schur multiplier is SP bounded to the following zero curvature condition. The zero curvature condition tells us that there are also neighborhoods U and V around my point, such that if I go now to any other boundary point here, let's say here, which is close to my point and still in the boundary, okay, let's call this point x1y, and let's put another point in the same box in the boundary x2y. So we have 2 points in the boundary. We have another point here, let's say this one. So I am assuming that these 2 points have the same second coordinate, y. Then I am imposing that the n2 part of my orthonormal vector have to be parallel. So this is some sort of zero curvature condition, meaning that when I move in certain direction along the boundary, certain part of my normal vector does not change the direction. It's a very, very relaxed form of flatness that I am imposing here. We will see that later. And this is equivalent to SP boundedness. And the third condition is an analytic characterization, which is not geometric anymore. And it says that around my point, x naught, y naught, I can find two C1 functions, F1, F2, in U and B, so that my domain in this box, so I'm talking about this region here, okay, my domain is this box, in this box can be characterized as those points xy for which F1x is greater than F2y. So if you think of it, this is reminiscent to the classical situation in dimension 1, in which you for instance, put value 1 here and value 0 here, in which you say that x has to be greater than y. That's the only condition, okay? So I am allowing C1 diffeomorphic deformations of this thing, but it is still, if you wish, a deformation of a triangular truncation. Okay, so these three conditions are equivalent. This is the main statement in a short way. And the first conclusion that we should get out of it is that Fefferman's original theorem falls into the setting of this result just by taking sigma to be a domain in Rn times Rn of the form x minus y belongs to omega for some Euclidean domain omega in n dimensions. Okay. In this case, this sigma is fully transverse, meaning that every point in the boundary has this transverse condition here that I was imposing, and it explains why transversality did not appear in the original formulation of Fefferman, but it's needed for this more general theorem. Okay. The second comment is that this theorem holds not only in Rn, but in any differentiable manifold. If you think of that, this is quite nice because differentiable manifolds do not have any Fourier transform connection. So this essentially is showing that the phenomenon discovered by Fefferman in his ball multiplier theorem extends well beyond the Fourier transform to other non-trigonometric scenarios. Okay, this is one important point. Another important point is that in this condition here, the condition of curvature that I was imposing is a C1 condition of curvature. But if I impose my domain to be C2, which is even nicer, then I can provide a second derivative condition. So if I call dx dy f of xy as the matrix in which I take x derivatives in the rows and y derivatives in the columns of my function f of xy, and f of xy is a C2 function, so that the level set of capital F is giving me back my domain, okay? Then the condition is that this multiplied by u and v in the kernel of dxf and dyf respectively has to be equal to 0. So this is the zero curvature condition in a C2 form, okay? We haven't found any instance of this curvature condition in the literature in the C1 setting, but in the C2 setting, if you go to Stein's harmonic analysis book, the thick one, the latest one, he introduced a notion of rotational curvature as the determinant of dx dy f, which is very much related to the one we are using in this talk, okay? I should mention that this dx dy, which is a cross derivative in x and y, is the right one, because if you look at dxx or dyy, this is not helping, because whenever you look at sets which only depend on x or only depend on y, no matter what is the geometry of these sets, this will be always LP bounded, okay? So it is the interaction between x and y which could have troubles, okay? So that's the nature of our result. So I think it's time now to talk a little bit about examples. Any questions so far? Okay. Okay, so I was saying that this theorem is a local theorem, but it becomes global whenever we let it act on fully transverse, relatively compact domains. Okay, in this case, we can say that the statement I have just given in theorem A is a global statement. And I should mention as an example that Fefferman's theorem tells us that we cannot find any a smooth, compact, Fourier idempotent in Rn, because if it is smooth and it is compact, it has to admit some curvature at some point. And then the ball multiplier the ball multiplier theorem imposes that it cannot be LP bounded. But we have plenty of examples in the non-Tablate case. And the most funny one is exactly the ball again. If you consider the ball in 2n dimensions, so that is x, y in Rn, so that x squared plus y squared is less than r squared, this is an SP-bounded multiplier because it satisfies trivially this condition here. Okay, this is trivially true in this case because you can separate variables here. Okay, so this is an example of how different is the Tablate and the non-Tablate worlds. Okay, another point is that the relative compactness that I am imposing in this statement in red is absolutely crucial at this point. We have counterexamples that for non-relatively compactness, fully transversal domains, the result is still true at a local level, but not at a global level. Okay, but that's one comment aside. So let's go to the main example.
Javier, can I ask something here?
Yeah.
So here you said theorem holds globally in the previous slides. So do you mean this U and V will be global instead of the local?
Yeah,
domain?
that means that this means that if you have a global domain which is fully transversal in the boundary, then if you have this condition here,
okay,
either 2 or 3, then the submultiplier is not only bounded in this box,
but
in
the
the full.
Okay.
Okay. Do you see now what I mean?
Okay, so it's not mean that there exists an U and V locally, but you can take the sort of full domain in this sense. Okay, that is automatic.
Exactly.
Okay. So is there any other example of this? Okay.
Sorry.
Is there any other example of domain like this where this is global phenomena happened? Except
yes.
So this is
any domain in which you can separate variables like this. It's good. Okay. So you can put any algebraic condition here in which no mixed monomials appear, and then it will give you an SP-bounded multiplier.
So, for example, ellipse, rectangle, and all this stuff, right?
Sorry.
For example, ellipse, rectangles, and all these domains will give you this kind of global phenomena, right?
Yeah. Okay. So now let me go to the spherical Hilbert transforms that I was addressing at the beginning, and I will not only impose xy inner product bigger than 0, but bigger than delta for any delta between -1 and 1, which are the possible values for this inner product whenever x and y are in the unit sphere. Okay, so this is what I call H delta. Okay, so the result is that whenever p is not equal to 2, the n-dimensional spherical Hilbert transforms are all SP-bounded in dimension 1 and all SP unbounded in dimension greater or equal than 2, no matter what is the value of delta. So this fully answers the problem, and the proof is easily seen with a picture. So if I pick x1y and x2y, my pair of points in my zero curvature condition, then what means to be in the boundary? To be in the boundary means that the inner product is equal to delta, not bigger than delta. So for an x1 point, the points in this red circle are the points in which this inner product is equal to delta. And for x2, the blue circle is the points in which x2y, in the inner product x2y is equal to delta. So in the intersection, we fix this y. So for this pair of points, you can consider either the tangent or the orthonormal vector to these manifolds, and you see that they are different no matter how close x1 and x2 are in my picture. So this means that I can never make this blue and red vector parallel unless x1 is equal to x2, meaning that the curvature condition fails, so that it has to be unbounded. Okay. So in this particular case, you can apply theorem A with a drawing to see that the spherical Hilbert transforms are not bounded. Okay. So that's an application of the theorem. Well, this being said, this is what we have done for Schur multipliers. And now the goal is to apply them to address the problem for Fourier multipliers on Lie groups. Okay. So let's go to this third block and final one. So what do we know so far about Fourier idempotents? We have already said that in the Euclidean case, semi-spaces or finite combinations of semi-spaces like polyhedra are Fourier idempotents. We can even have polyhedra with infinitely many faces if their directions are lacunary, but I'm not going to enter into this subtleties. But this being said, this is essentially all what you can say, because otherwise you would have curvature in the boundary. Okay, so this is almost a characterization in the Euclidean setting. In the non-commutative setting, we have some results in the literature. For instance, if we work with free groups, Bojetko and Fendler in 2006 proved that balls in the Cayley graph are not uniformly bounded. So this is a negative result which is reminiscent to the Fefferman's theorem for the ball, but they were able to prove it only for p greater than 3. For p between 2 and 3, it's still an open problem. And May-Ricard, very recently in 2017, in a remarkable paper, they were able to prove free analogs of the Hilbert transform using a non-commutative extension of Kotler identity for the Hilbert transform. So this is what is known about idempotents for free groups. For cross products of this form, so G is an orthogonal group acting orthogonally in Rn, then we consider the cross product of a directional Hilbert transform in Rn pointing in the direction of U, cross product the identity. Then what I was able to prove with Keith Rogers is that these operators, which are idempotents, of course, because this is a Hilbert transform, are only LP bounded when the orbit of the direction U under the group G is a finite set. So this is essentially a negative result, going back again to the obstructions posed by Fefferman's theorem for the ball. Okay. And another positive result is an extension of this idea by May-Ricard to other groups that I extended recently with a former student of mine, Adrian Gonzalez, and Julian Xia from Glasgow. Okay, so what is the problem? The problem is, how do we characterize Fourier Lp-idempotents on Lie groups? What is the shape of an idempotent domain leading to an LP-bounded Fourier multiplier if we don't know what flatness means in this case? Okay, so the solution is this result. If G is a connected Lie group and omega is a C1 domain in the Lie group, and G0 is a point in the boundary, it is equivalent that the characteristic function of omega is locally LP bounded at G0 to the geometric condition that the boundary around G0 is just the exponential image of a codimensional, a codimension 1 Lie subalgebra. So let me give you a picture of what I'm saying here. I have my Lie group here. Okay, I have the identity element there. I have my Lie algebra. And I have the exponential map. So, sorry, this should be this one. This is the exponential map. I have the origin here, sorry, the origin of the Lie algebra. And then I will consider a codimension 1 subspace, okay? If it is not only a subspace, but a subalgebra, okay, then it falls under the assumptions of my theorem. So let me draw the exponential image of this line here, or hyperspace, if you wish. So you have here some boundary. So what I'm saying is that if you put here 1 and here 0 in your Fourier symbol, then it will be LP bounded locally around E, okay, locally around the identity element, if and only if this thing here defines a codimension 1 Lie subalgebra, not a subspace, okay? It has to be a subalgebra. So, of course, this is all what you need to know, because if you consider any other point, G0, which is not the identity, Fourier multipliers are translation invariant. So you can move everything to the unit and do the same operation I have just drawn here, okay? So this being said, this answers what do we mean by flat. So this submanifold here is a flat submanifold because it comes from a codimensional 1 Lie subalgebra under the exponential image. Okay, this is the answer that we were trying to find. More than that, if the group is additionally simply connected, there is another characterization of that, which is that there exists a smooth action of G acting on the real line by diffeomorphisms, so that the domain omega around G0 looks like the set of points in the group, so that the action of G on 0 is greater than the action of G0 on 0. Okay, this is let's call it an ergodic, if you wish, characterization of the same property. Okay, this being said, we have given a geometric characterization of these things, but we aim for a group theoretic characterization of LP boundedness. Well, this is what I was saying. This unravels what Fourier boundary flatness means for Lie groups. But now let's go to the group formulation. So I'm going to consider 3 scenarios. The first one is the group G1 is the real line, and the semi-space of the real line is the positive real line. Okay. Then I will consider the group G2, which is the affine group, and the affine group is just the linear transformations AX plus B, where A is positive and B is any real number. And then I will consider the semi-space in which B is imposed to be positive. Okay, so that's another group with another semi-space of the group. And finally, I will consider the universal covering of PSL2 as my group, and I will consider the semi-space given by those points in the group whose action on 0 is positive, where the action that I am considering is the standard the lifting of the standard action onto the real line. The lifting of the standard action of PSL2 on the projective line to the corresponding universal coverings. Okay, so this being said, I have 3 groups with 3 semi-space of the groups, 3 halves of the groups, if you wish. So the Kotler identities developed by May and Ricard, and further developed by myself with Julian Sia and Adrián González, allows us to prove that these 3 settings give us LP-bounded Hilbert transforms, not only locally, but globally, okay? And what this theorem tells us is that these are all the examples that you can find in Lie groups up to directional extensions. What do I mean by that? What I mean is that if I am in a simply connected Lie group G, and omega p and g naught are as above, then the characteristic function of omega will define locally around g naught an LP Fourier multiplier if omega looks like this. So around g naught is the inverse image of some of these semi-spaces, one of these three semi-spaces, and where F is just a surjective homomorphism of my group G into one of these three groups. So if you think of the classical setting, in the classical setting, for instance, you have this, this Hilbert transform, which is 1 here and 0 there. But this is nothing but the Hilbert transform in this direction, which is the orthogonal direction, tensor the identity in this direction here. So I'm just saying that in this part of the line I get the value 1, and in this part of the line I get the value 0, and then I extend it to the full plane by the identity map. So this thing that I am drawing is a directional Hilbert transform out of the classical Hilbert transform in dimension 1. I can do it in R2, but I can do it in Rn. Okay. What this theorem is telling us is that for Lie groups, it is exactly the same case. Every Hilbert transform is a directional Hilbert transform coming out from a lower dimensional Hilbert transform in three possible models: the classical Hilbert transform, the affine Hilbert transform, and the projective Hilbert transform. So we have found only three models, which are set here in red, for Hilbert transform, out of which all the rest in Lie groups can be constructed. Okay. So just to finish, let me just mention that as an application of these results, which, well, this one is giving us a group theoretic classification, okay, we can say how these Hilbert transforms look like in simply connected nilpotent Lie groups, particularly in stratified Lie groups. The directions have to live all the time in the first stratum of this Lie group. Then we can also prove that for simple Lie groups, which are not locally isomorphic to SL2R, for instance, for high rank Lie groups, SL3, SL4, and so on, then there is no idempotent at all. There is no way to construct a Fourier Lp-idempotent in any possible way. And finally, when the group is locally isomorphic to SL2, there is a unique local Fourier idempotent up to left and right translations, which is given by, in SL2R, by the signum. Let me write it here. It's given by the signum of C, up to right and left translations. Okay? What it is significant is that we studied before this paper the Fourier idempotents in SL2Z, not in SL2R, and the right formula for this lattice is the signum of AC plus BD. And there is no apparent good connection between these two formulas. They cannot be related one to the other by a left or a right translation. So it is quite significant that the natural model for Fourier idempotent in SL2Z is not the same model that for SL2R, unlike what happens in the integer lattice Zn inside Rn, for instance. Okay, but this is just one more instance of how complicated is harmonic analysis in semi-simple lattices and semi-simple Lie groups. Okay, so this is all what I wanted to say. Thank you very much.
So, are there any questions from the audience? Hello?
Yes?
Are there any questions from the audience? So the thing is, do you use representation theory of SL2R, PSL2R in your work, or to study this kind of problem which you are talking about?
Whether I use representation theory to achieve these results? This is your question?
Yeah.
No, not really.
Not really.
The statement about SL2R, I should have mentioned this. This is important. The connection between theorem B1 and B2, so B1 is the geometric theorem and B2 is the group theoretic theorem, essentially follows from the following link. Everything comes from theorem A. So once you have a characterization of Schur idempotents, then you can relate them with Fourier idempotents in Lie groups, because we can transfer between Schur multipliers and Fourier multipliers, as I mentioned at the beginning of the talk, with this result here, okay? But this result works only for amenable groups, and I've been using non-amenable groups and non-unimodular groups in my talk. The key point is that this result is still true at a local level for non-amenable groups. So since my results are not, local, I can use transference for any group and relate theorem A with Fourier multipliers on Lie groups. Once this connection is established, theorem B1 follows directly from that, okay? And theorem B2 follows by a classification of which are the codimension 1 Lie subalgebras of a given Lie group. And to our surprise, this was already studied by Lie himself in the late 19th century. Okay, so it was very nice to discover that the work of Lie has implications still in the 21st century, because theorem B2 follows from theorem B1 exactly because of that. Okay, so this is all what you use in proving 2 and 3 here, because then you just have to identify which are the codimensional 1 Lie subalgebras of these Lie groups. And in the case of high rank simple Lie groups, there are none. And in the case of SL2R, there is a unique choice up to this left and right translation. Okay, so this is the proof that we use for SL2R, whereas for SL2Z, in that other paper, what we use is these Kotler identities, again not related to representation theory.
Mm-hmm. So if there are no more questions, so let us thank the speaker.
May I ask one last question?
Okay.
Just
Sure. Okay. Yeah.
So you said in the group level, for example, take SL2R, so you can define Fourier multiplier using regular representation. But there is also this Harishchandra Fourier transform in this kind of group, for example, SL2R. So if I define Fourier multiplier using this Harishchandra Fourier transform, so how it's related to the definition of your Fourier multiplier theorem here?
This is a very good question, and I didn't mention at the beginning of the talk, but I should have. So let me clarify that point. My definition of Fourier multiplier is this one here, but the idea is that I have L of G, which is my group for Neumann algebra. Let me think commutative for a second. So if G is an abelian group, this is just L infinity of G hat. Okay. So let me write like this. And I am working in G hat, let's say. And then this means that my multiplier is defined on G. Okay.
Yes.
So the symbol is defined on G. So this means that the action will take place in G hat where the frequencies live on G. Whenever you work with the Fourier transform that you are mentioning of Harishchandra, this is meant to work on G. And the frequencies live in the dual object of G. So you need the representation theory developed by Harishchandra to provide a good or rich enough information in understanding a Fourier multiplier in G, but not in G hat. So this is what has been done by Harishchandra, but later in the case of the Heisenberg group and many other groups of that kind, by Fulvio Ricci, Michael Cowley, many people, right? But what I am talking about is the dual formulation. So I want to study Fourier multipliers in the dual object by setting symbols in the group itself. So this was started, as I mentioned, by Hagerup in the late 70s because of its connection with geometric group theory and potential implications in the classification of group von Neumann algebras. So it has a lot of implications in rigidity theory of von Neumann algebras or group von Neumann algebras. But it's not so much related to the previous formulation that I was mentioning. Both problems are dual to each other, and there are some similarities that you can find. For instance, in both settings, we've been able to produce analogs of the Hormander-Miglin multiplier theorem and some other related results, but are different problems from the very beginning.
So, if I may, so that means sort of you're changing the frequency domain and the space domain interchanging, right?
Yes,
right.
Totally right.
But then if I may ask that, so here, if the multiplier defined in the space domain, like in the group here, so how the interpret this Fourier transform here, like TMA fat here? How do you make sense of that? Like, what is Fourier transform here?
The Fourier transform is let me write it here. So if I have an element f in L of G, so what is the Fourier transform of f at the frequency G? This is what you're asking, right?
Yes, yes. So,
well, this is the as in the classical case, this should be the trace, which is defined here. Okay, the trace playing the role of the integral of f times the adjoint of my character, but my character is the left regular representation, so lambda G star.
Okay.
You see what I mean now?
Yeah.
So that's my Fourier transform,
I believe. But in the case of Rn, it's an equivalent, I think.
In the case of Rn, you just recover the classical Fourier transform.
Okay.
Because in the case of Rn, lambda G is the operator by Fourier transform conjugation. You can realize it as a Fourier character. So these imaginary exponentials that we are all used to. So there is a way of relating this formula to the integral in Rn of f against the conjugate of the Fourier character. So you recover all the theory for abelian groups because they have this point gradient duality. For non-abelian groups, you have to decide whether you state things in group von Neumann algebras with frequencies in the original group, or you work in the original group playing or placing the frequencies in the dual object by using representation theory. So these are dual formulations which are not related one to the other. Okay.
Thanks for clarification. Thank you for your
talk. Are there any other questions from the audience? Okay, so if there are no more questions, let us thank the speaker for a wonderful talk. And
thank you very much.
I end this meeting now. Okay. So, okay. Again, thank you, Professor Javier. Okay,
thank you very much. Thank you to you all for your interest.
Yeah.
Bye bye.
Apurva, you have stopped recording.